Now, let us do the electric potential and capacitance. It is chapter 2 in NCERT 12th class textbook, volume 1. So, we'll do some more problems from Gauss law afterwards. I'll do one thing, I'll share you one assignment on Gauss law and applications. Later, I will share the hints and solutions, and one day we'll spare for any doubts, okay? That day we'll do. So now I'll be starting the electric potential and capacitance, the second chapter. So it's very, very important. Takes time to conclude, of course. Okay. So it is the NCERT 12th volume 1 second chapter. Electric potential and capacitance. So already I told you in the properties of electric charges that the physical state of a body as regards to electricity can be known with the help of the electric potential. So conceptually, it is the physical state of a body as regards to the electricity. So that is the physical meaning. Means whether the body is able to hold some more charge or not, or at what time the leakage of charge will begin. All these aspects relatedly, the capacitance also will come from this particular very important concept of electric potential. So the physical state of a body as regards to electricity can be called as the electric potential. And then the definition is, of course, very simple. So electric field, of course, is a conservative field. And before we go for the definition, you must know that before going for the definition, you must know that work done by the conservative force is path independent. So it depends only on the net displacement. What I mean is, suppose in the electric field we have 2 points C and B. Either the work is done by the field or we are doing work against the field. Both ways it is applicable. Whether you move the charge straight from A to B or in a zigzag path or in a well-defined path, whatever it may be, but it depends only on the displacement, not on the geometrical path followed. So that is a very, very important. Any conservative force, there is a gravitational force or electric force or magnetic force. Whenever you are doing work, why the conservative force is considered, then we must remember that it is path independent. It depends only on the net displacement of the body plus so here to introduce the concept of electric potential, the electric potential at any point in the conservative field, say electric field, can be defined as work done in displacing a body from infinity to a point, charged body, of course, per unit charge. Work done on unit charge in bringing it from infinity to a point in the electric field is basically defined as the electric potential. This is, of course, the quantitative definition, means the numerical measure of electric potential at a point can be known using this definition. I repeat, the work done in bringing a unit positive charge from infinity to a point in the electric field is defined as the electric potential at that point. So, SI unit. Let us go for the derivation of the formula and all in the next step. So, SI unit.
Sir, can you once repeat the definition again?
Yeah, you can note down work done in bringing a unit positive charge. Work done in bringing a unit positive charge from infinity to a point in the electric field. Work done in bringing a unit positive charge from infinity to a point in the electric field against the electrostatic repulsive force. Against the electrostatic repulsive force is defined as the electric potential at that point. Is defined as the electric potential at that point. Of course, right in the next line note, very important conceptual point. It can be asked even in exams. JE especially, he catches these type of points only. Note, work is done in bringing the unit positive charge without acceleration. Work is done in bringing a unit positive charge into the field. Work is done in bringing a unit positive charge into the field work is done in bringing a unit positive charge into the field without any acceleration. It can be also said as the energy spent. It can be also said as the energy spent in bringing the same. So SI unit is Joule Coulomb inverse. This is called volt. The actual name is Count Alessandro Volta. That's the actual name of the physicist who defined this particular quantity. So on his name, they put this unit as volt. Count Alessandro Volta. So the unit is volt because it is named after the scientist. It should be represented by capital V. Electrostatic units, it is ergs per stat coulomb. So this is stat volt. Dimensional formula, it is work done ml square t to the power of minus 2 by charge it. So it will be ml square t to the power of minus 3 I inverse. ml square t to the power of minus 3 I inverse is the dimensional formula for this electric potential. And here, you know, W infinity to P can be written as integral f bar dot dx bar infinity to P. So potential formula can now become 1 by Q naught, of course negative, because work is done against repulsive force. So it is minus 1 by Q naught into infinity to P into F bar dot dx bar. F bar by Q naught can also be put as E bar, force on unit charge. Therefore, it can be also written as V is equal to minus of infinity to P E bar dot dx bar or dr bar. Both are correct. Dx bar means only a long line, straight line, x-axis. Dr bar means you can apply even to the space. That's the only difference. Dx, if you say, you are confining only to x-axis. So the motion is only one dimensional. Dr bar means it can be 2 or 3 dimensional. So this is how we introduce the concept of electric potential. You can expect some problems, force and position vector, or electric field strength and position vector they can give you, and they may ask you to find the potential. All those problems we will do after we complete the potential difference and related concepts. Completed, huh?
Yes, sir.
Now let us derive the formula for electric potential. So let us consider a positive charge, and here is the field of it, electric field of it. Somewhere here we have the point P naught at infinite distance from the field, and here I have a test charge, positive test charge Q naught. Now the task is to bring the test charge and keep it in this electric field. So here is some point P in the electric field at a distance r from the charge considered. So repeat once again. We have an electric field around a point electric charge of plus capital Q coulombs. The task here is a point electric charge, the test charge of plus Q naught is at infinity at a point P. It is to be brought from infinity and placed at this point P. That is a task. So for moving it in the electric field, logically no need to do any work till it comes to the boundary of the field. But because the charge is brought from infinity, so conventionally we say the work is done in bringing the positive test charge from infinity to this point. So the electrostatic repulsive force will be, the need to do the work can be understood from this. The electrostatic repulsive force will be trying to push this positive charge away from the field because it is a positive field of positive charge. And the charge which we are intending to bring it into the field is also positive. Therefore, the positive test charge will be trying to push it away from the field by applying the repulsive force. So we need to apply a force which just balances this repulsive force. That's why work is to be done again is this repulsive force. So this charge is finally brought from infinity and is pushed to this point, say P. Finally, Q naught is at P. So you need to do some work, and whatever work we do in bringing that test charge from Q naught to, from P naught to P is, we'll call it as say integral dw. X1 is equal to infinity and x2 is equal to r. So according to the definition, the electric potential at this point is work done again is the repulsive force in bringing the test charge, unit positive charge, from infinity to the point at a distance r from the given charge. So this will be minus half integral f dx. X1 is equal to infinity to x2 is equal to r. Sorry, here it is r. Yeah. So because f is equal to fr, hence we will get the negative sign again, don't repeat it here. So we will be getting it as minus of q naught On unit charge kada q naught మర్చిపోయాం. 1 by q naught. So work done on unit charge is defined as electric potential. Therefore, it is integral infinity to r dw by q naught, that is minus 1 by q naught into integral f dx. So I get minus 1 by q naught into integral of q naught by 4 pi epsilon 0 x square into integral dx. So this q naught will cancel, and I am left with minus q by 4 pi epsilon 0 integral x to the power of minus 2 dx. Yeah, we'll do the derivation next. Please copy this.
Completed, sir.
Completed, huh?
Yes, sir.
Okay, good. So we'll be getting it as I'm applying the limits and all. So I get V is equal to minus Q by 4 pi epsilon 0 into integral x to the power of minus 2 dx. This is of course from infinity to r.
Sir, only x to the power of minus 2 only, no, sir.
Pardon?
Only x to the power of minus 2 only, no, sir. No minus sign inside integral, no, sir.
Yeah. Yes, yes. So this is minus q by 4 pi epsilon 0 into minus 1 by x. Am I right?
Yes, sir.
From infinity to r. Therefore, we'll get finally the electric potential at a point, because it is a scalar. We finally get it as q by 4 pi epsilon 0 r. V naught in vacuum, or V naught becomes equals to 9 into 10 to the power of 9 into q by r. Implies V naught varies directly as q by r. And if a medium is there, present between the charges, then we'll get V is equal to, of course, q by 4 pi epsilon r. Epsilon is k into epsilon 0. That's how finally I'll get 9 into 10 to the power of 9 by k into q by r. That is electric potential. If some medium is present in between the point of interest and the given charge, Completed, huh?
Yes, sir.
Completed, sir.
So here you can add one more point, put note and add. At x is equal to infinity, potential at infinity will be 0. Anything by infinity is 0. So at infinite distances from the given point charge, the electric potential will be 0. Vx graph. So this is the distance x and here is the potential. Due to a point charge only we are doing now. Because V varies directly as 1 by x, the graph should be a rectangular hyperbola. Completed, huh?
Yes, sir.
Then potential difference. Similar things would have come in gravitational lesson also. So next is potential difference. Here is a positive charge. And this is the boundary of the field. We have a point P naught at infinity. Where I have a positive test charge Q naught. And there are 2 points in the electric field. Let us call them as A and B at distances R1 and R2 from the given charge. Now, if you want to do work in bringing this test charge from infinity to a point A, then it will be WA. If the same charge is to be brought to the point B, WB. So the difference of works to be done, WA minus WB by Q naught, can be defined as potential difference. Or in other words, if you want to shift this positive test charge from the point B to the point A, then work done in bringing a unit positive charge from a farther point to the nearer point in the electric field, of course, again, this electrostatic repulsive force can be defined as the potential difference. In other words, Simple definition, the difference of electric potentials across any pair of points in the electric field can also be defined as the potential difference. Yeah, you can note down please. Definition. The simplest definition first, let's write. The difference of electric potentials, the difference of electric potentials across any pair of points, across any pair of points in the electric field, across any pair of points in the electric field will be equal to the potential difference, will be equal to the potential difference, or next slide, another definition, the work done in shifting, the work done in shifting a unit positive charge, the work done in shifting a unit positive charge across a pair of points in the electric field, across a pair of points in the electric field against the electrostatic repulsive force, against the electrostatic repulsive force is defined as the potential difference, is defined as the potential difference across those pair of points, across those pair of points. Right in the next line, note the electric potential and potential difference are scalars. Note the electric potential and the potential difference are scalars. So let us try to write the formula for it. So it is VAB. So as per the definition, it is minus 1 by Q naught into integral dW from x1 is equal to R2 to x1 is equal to x2 is equal to R1. That is from B to A. So it can be also said as minus 1 by Q naught integral f dx. Limits are from R2 to R1. So it will be equal to WB minus WA by Q naught. Sorry, WA minus W. WA minus WB by Q naught. That is equal to VA minus VB. WA by Q naught is VA. WB by Q naught is VB. So we can write it as Q by 4 pi epsilon 0 into 1 by R1 minus 1 by R2, or 9 into 10 to the power of 9 into 1 by R1 minus 1 by R2. So this is the formula for The
Sir,
potential.
you forgot Q, sir.
Pardon, ma? Yeah. Right. So many volts. So WB by Q naught is work done in bringing unit positive charge from infinity to the point B. WA by Q naught is work done in bringing a unit positive charge from infinity to the point A. So WA minus WB by Q naught is nothing but potential difference across those pair of points. Or as I said, work done in shifting a unit positive charge across any pair of points in the electric field. That can be also defined as the potential difference. Read it.
Yes, sir.
Superposition principle, similar to the electric field and force. So just as we said there, it is the space, and this is a continuous charge distribution with different charges. Continuous charge distribution means if the separation between any pair of charges is negligible relative to the mutual separation between them, if the distance of if the distance of the point of interest is relatively larger, or if their distances from the origin are relatively longer relative to their mutual separation, then that particular charge distribution is called as the continuous charge distribution. So these are the charges Q1, Q2, Q3, etc. And this is a point P. These are the distances R1, R2, and so on Rn. So the electric potential due to this continuous charge distribution at a particular point, electric potential at a point due to a continuous charge distribution V is here the algebraic sum of potentials at that point due to the individual charges. Why we are telling algebraic sum? Because potential is a scalar. So it should be algebraic sum. If it is a vector, vector sum, because electric potential is a scalar, it should be algebraic sum. I repeat once again the statement. The electric potential at a point due to a continuous charge distribution will be equal to the algebraic sum of electric potentials at that point due to the individual charges. If you want, you can write it. Superposition principle statement. The electric potential at a point in the electric field, the electric potential at a point due to the electric potential at a point due to a continuous charge distribution, will be equal to the algebraic sum, because it is scalar, the algebraic sum of electric potentials, algebraic sum of the electric potentials at that point, algebraic sum of electric potentials at that point due to the individual charges. Algebraic sum of electric potentials at that point due to the individual charges. So you can note it down. So V is equal to sigma Vi, I is equal to 1 to n. So it can be written as V1 plus V2 and so V3 and so on Pn. Therefore, we can write the formula for electric potential as, yes, assuming that there is no medium, directly writing is the 1 by 4 pi epsilon 0. I'm writing 9 into 10 to the power of 9 into Q1 by R1 plus Q2 by R2 and so on Qn by Rn. Yeah, you can make it capital Q. Or you can also write it as V is equal to 9 into 10 to the power of 9 sigma I is equal to 1 to n Qi by Ri. Here we also get for the symmetric charge distribution, that is R1 is equal to R2 and so on, Rn is equal to R. We get V is equal to 9 into 10 to the power of 9 by R into sigma Qi. So this is the superposition principle. Problems on this will be normally very simple because it is just algebraic sum. Only care you should take is if the charge is positive, potential is plus. If the given charge is negative, it should be minus. That care you must take while attempting the problems.
Completed, sir.
Okay. Yeah, you can try some simple problem based on this. You have a point electric charge of some 50 nanocoulombs. You have a point P at a distance of 5 centimeters. So you wanted the electric potential due to this charge at this point. So simply V naught is equal to 9 into 10 to the power of 9 by Q by R. So it is, we are starting from the basic concept of potential. 9 into 10 to the power of 9 into 50 into 10 to the power of minus 9 by 5 into 10 to the power of minus 2. So 9 minus 9 cancelled. This is 10. So it is 9,000 volts, or simply 9 kilovolts. Based on this, you can try another one also. Let us take the same charge of 50 nanocoulombs, and we have 2 points in it. One is P at a distance of 5 centimeters. Other is Q at a distance of 10 centimeters. So you wanted the potential difference across this pair of points, VPQ. So it is 9 into 10 to the power of 9 into Q into 1 by R1 minus 1 by R2. So 9 into 10 to the power of 9 into 50 into 10 to the power of minus 9. Because R1 and R2 both are in centimeters, 10 to the power of minus 2. 1 by 5 minus 1 by 10. So it is 4,500 into 1 by 2. Please check. So it is 2250 volts is the potential difference across those pair of points. Simple, direct concept based.
Sir, it's 4,500 into 1 by 10 also. 4,500 into 4,500 into 1 by 10 also.
Yeah, it's 1 by 10, correct. It's not square, is not there, na? So 4,500 is correct only. Okay.
Yes, sir.
Into 10. Good. So 2250. And we have another charge of say 60 microcoulombs. And we have 2 points in it at distances of 12 centimeters, 18 centimeters, and 12 centimeters in the field. So a ball to test charge of 2 microcoulombs is to be moved from B to A. Then you wanted the work done. So potential difference is W BA by Q naught. So work done is VAB into Q naught. That is of course direct formula 9 into 10 to the power of 9 capital Q into Q naught into 1 by R1 minus 1 by R2. So many joules. Yeah, you can remember this formula for work done in moving a test charge across a pair of points in the electric field. So this will be 9 into 10 to the power of 9 into 60 into 10 to the power of minus 6 into 2 into 10 to the power of minus 6 centimeters to meters 10 to the power of minus 2. No, here it should be 10 to the power of minus 2 only is correct. It should be 45,000, 22,500. That's correct only. Centimeters to meters 10 to the power of minus 2. Na? So LCM 1 by 12 minus 1 by 18. Here 36 is LCM. So 10 to the power of minus 12. 9, 10, 12. 10 to the power of 9, 10, 12. Minus 12 is cancelled. So you are left with 9, 6, 54, 108. 36 is LCM. 3 minus 2. This is 3's. So work done is 3 joules. Simple concepts. Superposition principle and all, tomorrow we'll see. So try some problems based on these simple concepts, superposition principle and all, tomorrow we'll attempt. Okay?
Yes, sir.
Yes, sir.
Thank you, sir.
Okay, Ramakrishna, I'll see your problem today.
Okay, sir.
Not finding time. I was in Hyderabad on Saturday, moving here and there, and some personal work. I came there. So I tried that day, but I could, phone net did not work out. So I could not take the class. And yesterday and today, of course, I was waiting for your principal's consent. Morning, he called me and he kept in morning. We'll see. Okay. Bye. Tomorrow I'll continue.
Yes, sir.
Okay.
Thank you, sir.
Thank you, sir.